Hi, we start chapter 12, linear models. So this chapter includes miscellaneous extensions and diagnostic methods for linear models introduced in chapters 6, 7, and 11. So this is a wrap-up chapter for the most important chapters, the 6, 7, 11. Okay, so 12.1, the polynomial regression. So we have considered multiple linear regression and always the relationship between y and the x j is linear. Excuse me. But here, we only think about y and x for now, but we think about the y is a polynomial of x. So we can express the more complicated relationship between x and y. Especially if we only have the finite range, it's pretty flexible if we can fit the model such as this. So this may be the quartic function, maybe the polynomial with degree 4. So we can think about that function. Y is equal to beta naught plus beta 1x plus beta 2x squared plus up to beta sub k x to the kth power plus epsilon. So still, the estimation is just as easy as the multiple linear regression because the estimating beta, as long as this function is linear in terms of beta naught to beta k, that it should be totally fine to estimate these parameters. So just you can see that the x squared, but this is just the same as the second predictor, and this is the case predictor. So this is called polynomial regression. So just the multiple linear regression, the theory, multiple linear regression theory applies. Yeah, so when we say linear model, originally we think about y is equal to a plus bx plus epsilon, and this is a linear function of x. But the more important thing is that this is linear in terms of AB, or the equation in this slide, linear with respect to the beta naught to beta k. One possible numeric problem is that if we include the x to the higher power, like the 5th power or 6th power, so that converges, that diverges to infinity pretty fast. And also, even if the shorter range, for example, x to the 4th power and x to the 6th power are really similar on x is between -1 and 1, for example. So sometimes it's good to have more orthogonal vectors. So if the correlation between x and x squared and x cubed, those are smaller, that's better. So sometimes we have orthogonal basis. For example, if first one is this and the maybe second one is this, then the third one, I don't know, but the x cubed may not be the best solution, best the variable. So maybe we want to have the cubic function which is distinctively different from the first two. I don't know what is the best one, but for example, this kind of function is at least better than the x cubed. Yeah, so the polynomial regression is more flexible than just regression with only x as predictor. But if the relationship is monotone, at first we have to consider the transformation of x or y. So think about the case that the plot are obviously different from linear, but monotone. In this case, probably we would like to fit, rather than the fitting the So rather than fitting the polynomial regression with degree 2, probably we can fit the square root of y on x. Then probably the relationship becomes linear, and we only have to use the two parameters, intercept and the x term. So that should be better. So at first, try transformation if the relationship is monotone. But if the relationship is much more complicated, such as this, then we have to think about the polynomial regression. So transformation can be done by logarithm exponential power function, or Box-Cox transformation is a kind of the automatic method which optimizes the shape of the monotone function. Yeah, so this is one example, the temperature and income by state. So average temperature X and the per capita income Y by the contiguous, the 48 states, they may not have the linear relationship. Maybe the warmer area have a larger population for the low income class, while the too cold areas cannot attract good industries. So, you know, in the warmer areas, it's easier for example, the people without houses can live. So possibly that we have more poor people, which makes the income lower. And the colder area, obviously, that they have the trouble to attract industries. So we think about the two model. So y is equal to beta naught plus beta 1x plus epsilon, and the alternative, the y is equal to the same terms plus the quadratic term. And okay, so this is the graph for two models, and the fitted line, the fitted curves are indicated as straight line for the linear and the dashed line for the quadratic. And maybe it looks this kind of curve, but it's not really clear. And actually, the quadratic curve is here. Estimated quadratic curve is here. Okay, so at first, the usual linear model with only this temperature as predictor. Then we can fit, and then temperature is obviously, I mean, they're clearly significant, so the negative. So actually, the warmer state have higher income per capita. Yeah, and yeah, maybe you can see what's the fit. So residual standard error, 7,483. So basically, typically, we have the error of the $7,400. And adjusted R square, 0.1153. Non-adjusted one, 0.1341. Okay, so and AIC, 996.5. Okay, so suppose we include the quadratic term here, then actually this isn't really significant, but actually we have some multi-collinearity. Yeah, standard deviation for this is obviously the inflated. So we are not exactly sure, but some trouble. And we calculate adjusted R square and the multiple R square. And these are actually slightly better, obviously, the multiple R squared always better for a larger model, but the adjusted R square slightly better. But if we calculate AIC, that is basically the model for prediction performance. Actually, the 996.9, that is larger, so that is worse. AIC smaller is better. AIC is basically negative 2 times log likelihood plus some adjustment term. So this is worse than previous one. So even though the adjusted R square is slightly better, yeah, slightly better. This is model 2 and model 1, but the AIC is better for a smaller model. So maybe it's a little bit confusing, but this is model for model 2, and this is for model 1. And this is for model 1, and this is for model 2. So AIC, it's better for model 1. So probably the linear term is enough. So the the temperature is enough, and the temperature square isn't really necessary. That is the conclusion of this analysis. Yeah, generally speaking, it's not really easy to find an example that the polynomial regression works well. So yeah, so if you find one, that's pretty interesting.